This is part 6 of the series Parallel and Perpendicular Lines. In the last part, we discussed parallel lines and transversals. We looked at how to determine if two lines are parallel if cut by a transversal. In this part, we're going to begin by looking at the different perpendicular line theorems. We're going to look at what happens and what the consequence is of two lines being perpendicular and how to determine if two lines are perpendicular. So the first thing, we're going to look at the perpendicular linear pairs theorem. The perpendicular linear pairs theorem says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So here we have a pair of lines intersecting, and it forms a linear pair, and these two pairs of angles are congruent angles. Well, we know that linear pairs are supplementary, and if linear pairs are supplementary, then their measures add up to 180 degrees. Well, if these angles add up to 180 degrees and they're congruent, then each angle must be a right angle, and therefore this line must be perpendicular to this line. So by the definition of perpendicular lines, two lines are perpendicular if they intersect to form a right angle. Well, both of these are right angles, so these two lines are in fact perpendicular. So that's the perpendicular linear pairs theorem. The next theorem we're going to talk about is the perpendicular transversal theorem. And the perpendicular transversal theorem says, in a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other line. Now, we're going to look at the proof of this a little bit later, but the idea behind this theorem is fairly straightforward. You can see that these two lines being parallel, having this as a transversal, and we're already given that this angle is a right angle. Well, we know that if these two lines are parallel, then the consecutive angles must be supplementary, the corresponding angles must be congruent, alternate interior angles must be congruent, and so on. Well, if this is already a 90-degree angle, and these two are supplementary, then clearly this angle has to be a 90-degree angle, which makes this line perpendicular to that. So that's a basic idea for one of the ways to prove this perpendicular transversal theorem. All right, the next theorem we're going to talk about is lines perpendicular to a transversal theorem. In lines perpendicular to a transversal, it says, in a plane, if two lines are perpendicular to the same line, then they are parallel. So here we have two lines perpendicular to the same transversal. That means these two lines must be parallel. These two theorems are very, very closely related, and they're very often confused with each other. And the important distinction between these two theorems is the fact that in one, we have two lines are given as parallel, and in the other, two lines are given as perpendicular. So that's the difference between the two. If you find it difficult to memorize the names and associate them with the theorem, that's okay, because it's really only important that you can paraphrase the theorem. So here, if we have two parallel lines and one is perpendicular to the transversal, then the other must be perpendicular to the transversal. Here, if you have two lines that are perpendicular to the same transversal, then those lines have to be parallel. Either way you recall it, it's really not important. The idea behind these is important. And also remember, both of these theorems can be very easily proven using the theorems that we just got finished talking about. The corresponding, consecutive, alternate interior, alternate exterior angles theorems and their converses. So that gives us three new theorems. And the primary purpose behind these theorems is just to give us a little bit more of a shortcut to solving other proofs that we would have moving down the line. And there's one more theorem that's very closely related to these that would also be an assist in other proofs, and that is the four right angles theorem. And the four right angles theorem says, in a plane, if two lines are perpendicular, then they intersect to form four right angles. And the proof of that one is fairly straightforward. You know that if this angle is a right angle, these two are vertical angles, so they must be congruent, so you have two right angles. Since these two are a linear pair, these two have to be right angles, because if this one's 90 degrees, that one has to be 90, and this one is vertical to that, so these two have to be congruent. So that's a very basic skeleton proof of the four right angles theorem. So these four theorems are just useful shortcut theorems to help us in future proofs. Now let's move forward and let's prove a couple of these theorems to see where they come about and to get a little bit better practice in our techniques in executing proofs. The first theorem we're going to prove is the perpendicular linear pair theorem. And here we have the same picture, two lines intersecting to form a congruent linear pair, and we're given that angle 1 is congruent to angle 2. So I've gone ahead and written the given down. We have to prove that line L is perpendicular to line M. So the plan for this proof, we need to show that these two lines are parallel, which means we need to show that one of these two angles is a right angle. In order to show that, we're going to use the fact that these two angles are a linear pair. And we know that linear pairs are supplementary, which means that they add up to, their measures add up to 180 degrees. So if these two angles add up to 180 degrees, and they're both equal to each other, then that must mean that they're both 90 degrees, and that must also mean that they're both right angles, and therefore these lines are perpendicular. So that's the general overall thumbnail sketch of our proof. Now let's see how to put that down on paper. Now the first thing we said was that these are a linear pair and therefore they're supplementary. So that's what we're going to say. So we're going to say angle 1 is supplementary to angle 2. We don't need to say that they're a linear pair. That's kind of an obvious statement. But we need to state that those angles are supplementary. So now that we've stated that these are supplementary angles through the linear pair postulate, what does that tell us? It tells us that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees, because that's the definition of supplementary angles. So that's going to be our next statement. So now we have the measure of angle 1 plus the measure of angle 2 equals 180 by the definition of supplementary angles. Now we have to figure out where to go from here. Now one of the things that strikes me is we haven't used all of our given information. We were given that angle 1 is congruent to angle 2, but we didn't do anything with it yet. What does that mean, that angle 1 is congruent to angle 2? Well, what that means, for two angles to be congruent, it means that their measures have to be equal. So that's another piece of information that we can use. And if I'm looking here and I see that two angles are being added together, that may be some critical information that we can use to manipulate this statement. So that's what I'm going to do, is I'm going to use this statement because I know that these two angles are congruent. By the definition of congruent angles, their measures are equal. Well, now, as I see these things written down here, I see that we might have something we can do. If we can actually substitute this angle 1 for this angle 2, then I would have angle 2 plus angle 2 equals 180. And that gives me 2 times the measure of angle 2 equals 180. And it looks like if I divided by 2 on both sides, then I would end up with angle 2 equals 90 degrees. And that gets us exactly where we need to be. We need to be to the point where we've said that one of these two angles is equal to 90 degrees. So that's what I'm going to do. I'm choosing to substitute the fact that the measure of angle 1 equals the measure of angle 2, so I'm going to substitute angle 2 in for this angle 1 in this expression. And that's the substitution property of equality. Well, now I can simplify this expression, combining like terms, and we have 2 times the measure of angle 2 equals 180. Now you could have said simplify or combine like terms or whatever valid mathematical reason you want to use for that, but the easiest way to do this is just to say simplify. Well, now remember, we had to get down to the point where one of these two angles was equal to 90 degrees, and to find the measure of that angle, we simply divide both sides of this equation by 2. And that's the division property of equality. So we divided both sides by 2, and we've got to the point now where we said the measure of angle 2 equals 90 degrees. So what does this statement tell us? Well, it tells us that if the measure of angle 2 is 90 degrees, then angle 2 is a right angle. And that's the definition of a right angle. Well, since we now identified that angle 2 is a right angle, then by the definition of perpendicular lines, line L must be perpendicular to line M. And that will be our last statement. And we'll scroll this up a little bit, and that will be the statement that we put in there. So because angle 2 is a right angle, by the definition of perpendicular lines, the symbol obviously means perpendicular, line L is perpendicular to line M, and that's what we were looking for. Now that's a little bit longer proof than what we're used to, and a little bit more logic than we've had to go through in the past, but I think if you have trouble with this, go through it again, but you should be able to see that as each statement was written down, these definitions led us to the next statement that we had to make. We asked ourselves the question, what does this mean? What does this mean? What does it mean for two angles to add up to 180 degrees, and so on and so forth? So asking yourself these questions is the way you lead yourself through the proof and determine, have I used all my information? Am I leading towards the thing that I'm trying to prove? All these things have to be kept in mind when you're executing proofs. Well, that'll wrap up this session, and I will continue with the next two proofs at the beginning of the next session. So I will talk to you in the next video.